Live again. Coming back at you. Episode 6 of the ZKDL camp. That's Zero Knowledge from Distributed Labs. They made some lecture notes on learning about zero knowledge. Me and Jessie are going through them as fast as we think is reasonable, which is kind of slow. So episode 6, and we are on page, 34?
33 is exercise 6.
Yeah, exercise 6. So we're going through the exercises of modular arithmetic. After this, if we can get through them, which we probably won't, then what the content next will be Introduction to Abstract Algebra, which I think will be way more fun and enlightening because I'm probably better at that. I hope. But yeah, exercise 6. Let's see what we got here. I'll read it. In the quadratic polynomial, f of x is equal to x minus p squared minus p, x minus q plus x squared minus qx. Okay. P and q are distinct prime numbers, both less than 10. This polynomial can be rewritten as f of x equals 2 to the quantity x minus r1 times quantity x minus r2, where r1 and r2 are the roots of f. If both r1 and r2 are prime numbers, what is their sum, r1 plus r2? Interesting. Don't remember learning anything about this in this section, do you?
No. So I wonder if there are lemmas that are like
the Mersenne primes
that talk
or
about adding prime numbers. So let's think about prime numbers. Let's just say like 2 is a prime number, right? So 2 plus 2 is 4. 4 is not a prime number. So what are we supposed to say? What is their sum, r1 plus r2? Can I just say like they...
Well, they're both prime numbers less than 10. So what are the prime numbers less than 10? You got 2,
so 2, 3, 5, 7.
That's it?
Yeah, I think that's it.
Okay,
yeah.
So there's our...
So 2 plus 2 is 4. 3 plus 3 is 6. 5 plus 5 is 10. 7 plus 7 is 14. All right, so they're all not prime. Is that it? Is that the answer?
If both r1 and 2 are prime numbers, what is their sum? Does it say their sum needs to be?
Oh, 7? Look.
The roots. So r1 and r2 need to be roots.
Oh, hold on.
So you need to satisfy the top equation.
Yeah.
Oh, it's rewritten, so it's the same thing.
Mm-hmm.
There's no P and Q. Okay, hold on. Let's write this out because... So f of x equals x minus p squared minus p. Blow this over a little bit.
Okay, I see. Can you just plug in p is 2 and q is 3? So it'd be x minus 3 squared minus 3 times x minus 3. Can you write that out on your...
Well,
can you also link me the Miro board so I can write it out too?
Yeah, sure.
Get a little bit of wrist action.
Copy board length. Coming at you.
Let's remove that for now.
And also equal to 2x minus r1 Okay, so P and Q are distinct prime numbers, both less than 10. It says nothing about the roots. Oh, just only that they're primes, not that they're less than 10. Potential primes.
1 second, my tablet's not connected yet to the Wi-Fi. Thought it was. Do we publish the Miro link at the end of each video?
It's the same Miro.
Yeah, but I'm just saying, do we? Oh, we don't. Okay.
We don't. I've yet to do that. We could.
Maybe
fuck this thing up. We make it editable, they'd just be destroyed.
Yeah. Maybe just for viewer only or something like that. We work on the same scratch paper. Okay, I'm just going to work on the right side of your stuff. Blow this up. Okay, so I have no, don't go back. I don't have the. Oh, you already wrote it. All right, I'll just copy yours. F of x is equal to x minus p squared minus p times x minus q plus x squared. Oops. Can I erase it? Nope, can't erase like that. How do I erase on here?
You have to choose the erase tool.
Oh, I just hit the undo. That's faster. Okay.
Yeah, it's easier. That's fine too.
X squared.
Undo will do a single brush stroke or a single pen stroke.
You wait, what? What'd you say?
The undo will just do an entire brush, whatever your last brush.
Yeah.
Stroke is.
Yeah, that's all I needed. All right, so P is equal to 2 and Q is equal to 3 because they just said they're distinct prime numbers less than 10. So I'm just going to make it that. So let's do that. So f of x is equal to, and I know that they gave us the other format, but I'm going to simplify it so that I can plug in my own P and Q. And I'll save the roots. I'll solve it like a system of equations, like 2. So let's see. So x minus p is 2 squared minus 2 times x minus 3 plus x squared minus 3x. All right. So now I get, I'll just write this out so I don't fuck up the algebra. All right. Oh, wait, hold on. Let's do it like this. All right. And then just simplify it like this. And then further simplify it like this. Minus 6x plus 4. Oh, let's do minus 2. Minus 3x. Hopefully I didn't drop a term there. I think I'm good. All right. So now I have that. And now my other equation with the roots was what was that one? What was the roots?
Can
go back to page 33. Oh, you got it there. Okay. I'll just grab it there. So you got, wait.
2 x minus r1 times x minus r2.
Is it really that? Hold on. Let me just double check.
Yeah, that's what I'm saying. We're looking for the roots.
Okay.
You can solve that first one equal to 0 to find roots.
Yeah. Hold on. Give me a second. All right, so this is your other equation. So this is equation 1. This is equation 2. This is f of x still. All right, so now let's do, can I factor that? No, it gets a weird fraction.
It's a quadratic equation. Find the roots. That's the first one.
No, it's true. You want to? Can we just plug it in a calculator? Because I don't really want to do. I just don't want to do it. Do you have a calculator, or do you want to use Wolfram?
No, you can.
All right, I'll use ChatGPT. The math should be fine for it now. Doesn't suck as much as it used to.
You only get X's?
Me? Because I plugged in Q and P, or P and Q. See, I made this.
Oh, forcing it. Oh, you just made. Okay. Got it.
Yeah. Oh, hold on, let me just take a screenshot of this. Can you move your cursor so it doesn't get in the screenshot I'm about to take? Yeah, thanks. And then solve this function, this quadratic function for x.
Are the answers to the solutions in the back of the book, you think?
They said something about something like there's an appendix, right?
Yeah, Sigma protocols.
Oh, your cursor is in there again. I have to retake the screenshot. It didn't populate in my clipboard.
It's your cursor.
No, it was yours.
Okay, whatever.
I'm having like an issue with the new Windows 11 copy paste function is like botched now. There it goes. That one worked. Use snipping tool.
Okay. There's the answers. The answers are on page 294.
Okay. All right. So it gets A is equal to 2, B is -9, C is -2. The discriminant is 97. Oh, that's not a nice solution. It's 4.712. The roots are 4.712 and -0.212. 0.212. That's not helpful. I guess I could plug in both. Okay, so let's say plug in both solutions for. Actually, can this be negative, or we're only taking the positive? I'll just say plug in both solutions for x in the second function. Solve for. I should have said solve for R1, R2. It's doing it.
Yeah, you can just set them equal to each other and solve for R1.
Yeah.
And R2.
It says plugging either solution. No, that's not. It misunderstood what I wanted it to do. It plugged in x for R1 and x for R2. It's not what I wanted. Solve for R1 and 2.
Go back to the thing. 294. I know the answer. This is doing it.
Smash the coefficients. -2 R1 plus R2 is equal to -9. R1 is equal to 9 halves. 2 R1 R2 is equal to -2. R1 R2 is equal to -1. So R1 and R2 are the two numbers whose sum is 9 halves, and the product is -1. Let T be one of the roots, then it satisfies. Yeah. It's solving.
You're using Claude.
ChatGPT with thinking. 5.2 thinking. So what is the answer?
10. C.
That's not what I got. I'm doing this wrong then. Okay, so how does it want us to do this?
It says you can set them both equal to 0 and solve.
Okay.
So you have two equations.
Okay.
It's like x equal to r, and then let's say down here. Scroll 24. So it's 6. Find the roots of f. Yep. By equating f of x equal to 0, you get two solutions.
Okay.
Two equations, two solutions. So R1 is equal to P, and R2 is equal to P plus Q over 2. And then you just, I guess, plug and chug from there.
I see. So I didn't need to plug in values for P and Q. No wonder I got 0. I could have just
So you
solved this.
say, basically, like your example was wrong because it didn't equal one of the options, I guess. Like it's you just solve for. Like, I mean, whenever you're looking for roots, you just set equal to 0 and solve.
No, the reason why mine didn't work was because it set everything equal to 0 essentially.
All right. 7. Suppose that P is an arbitrary prime. What is tau of P to 100? The fuck is tau? Oh, there it is. Define function tau of n. The number of positive divisors of n. That's what the tau of n.
Okay.
For example, the number 12 has 6 divisors. 1, 2, 3, 4, 6, 12. So T of 12 is equal to 6.
So including
Makes
itself.
sense. The number of divisors. Got it. In fact, following definition 3.25 notation, if n is equal to the product from j equals 1 to r of p sub j ace to the a sub j, then the following holds. Tau of n is equal to the product the same to a of j plus 1. For example, since 12 is equal to 2 to 2 times 3 to 1, we have alpha 1 is equal to 2, alpha 2 is equal to 1. And therefore, T of 12 is equal to 2 plus 1 times 1 plus 1 equals 6. So as I guess you can decompose these things into their constituent divisors. That's interesting. So we need to decompose P100. Which we did through, was it Chinese remainder? How did we do that? Euler's theorem?
One second. I'm still trying to understand how they got the 12 equals 2 squared times 3 to the first power. So tau of 12 is equal to 6. In fact, following definition 3.25 notation, if n is equal to the product from j equals 1 to r, p sub j to the alpha sub j. So p is...
That's from up here.
Where?
No, this is something we did learn about. Is Chinese remainder theorem, maybe? No. Here we are.
Looks P.
Yeah. Well, there's Toshin theorem.
Euler's Toshin.
For any number,
5
primes times their alpha, general formula for Euler's Toshin theorem is this. So you're deconstructing a number into its prime composition, which is a prime to some exponent times another prime to some exponent. When you have that, you can then use that tau function to break it down. So like,
wait, it says definition 3.25. What page is that on?
Definition.
It's like way up. It referenced that, didn't it?
Where?
This is 3.25. So it's up here, actually. Fundamental theorem of arithmetic is what they're referencing on page 24. So it says any integer n is greater than 1 can be decomposed in the unique way into a product of prime numbers. So P1 alpha 1, P2 alpha 2. Product of primes from j equals 1 to t, p sub j.
Yeah, so this is saying the tau function is
Okay, let me go back down to the
can be
page where we
done
have-
as, so you could get that. Then the tau function is just the product of those things.
Uh-huh.
So you take all the alpha j's. It's the product of the alpha j plus 1. So like if you can make that p, if you can deconstruct the number. So basically we have p of, oh shit. What is this, 7?
I need to take a snippet of that and then put it in the Miro, and then I can work
P
it.
of j alpha j.
Here. Grab this.
So it's asking for p of 100, right?
Put it over here. Can I
Tau
not
P
paste
100?
in?
So we're going to decompose 100.
Paste.
Or is it
Control
just,
V. What?
isn't it just, oh, just 101? I think it's just 101. Because it gives us the p.
Yeah, what is P12?
P is 100. It gives it to us. Tau of p of
Hold
p
on.
to 100.
Hold on.
And it's just alpha j. Alpha j is 100.
Okay.
It's 101. I thought it was like, yeah, I think it's kind of trivial for this one. We're expecting it too much. It's not a number to the 100. It's just fucking, it's saying like, what's alpha j in this thing based on this definition?
Oh. Yeah, okay. 100. 101.
Okay. Well, that was easier than we needed. Maybe.
Do you have the index pulled up with the solutions?
Yeah, I can just rotate. Here.
Is there like an alt tab version when you're going through a PDF in a browser so you can flip back and forth?
Sure, you use the browser better.
Let's see.
Or use a PDF viewer better. Let's see, 7. Yeah, 101. We only have alpha 100, which by definition is a function. Alpha's 1.
Yeah.
101. So it's
I see.
what we thought it was.
So it's the same. You're just using that tau function for all of them? So it's just
I think the next one's going to be harder. You actually have to do something. So like some integer in such that tau.
No. Exercise 7, B. Oh, I see. It's B. Never mind. I'm retarded.
Yeah.
Exercise 8.
equals
Suppose some integer
7.
n. We have tau of n equals 7. What is tau of n squared? Okay.
So there's 7 divisors. Hold on. The tau of n is 7. So there's 6 divisors.
So it's
whatever
6 plus 1,
n
right?
is.
So
if like, so we have n
so
is equal to the product of I is equal to, was it like
1,
J
2,
to
3,
R
4
of P sub j alpha sub j.
2.
And this is equal to like that means that tau of n is equal to the product, it's just alpha j plus 1. So alpha j is equal to 6. Oh no, that's not right. You can't tell off the top. It's the product of alpha j plus 1, which is equal to 7. We just did the so it's this prime number. If it's prime, I don't think it matters.
Interesting.
My intuition would be 14. I have no idea if that's right, just because that's why typically when you're dealing with exponents, you add them, but that feels not right.
So I just ChatGPT'd it.
Yeah.
So I got so if you have tau of n is equal to 7, you know that alpha sub j is 6. So like I got that far. And then you know that n is equal to p to the 6th power because alpha sub j is 6. And then you just take n squared. So you're just taking p to the 6 squared. So it's just 6 times 2. You get p to the 12. And then if you put it back in that format, tau of p to the 12, it's 12 plus 1, so 13.
Okay.
That's where I got lost, is putting it back into tau of p to the 12 power. And then you just go back to the format, 12 plus 1. Yeah.
Share your screen.
Yeah, here. I'm just going to put it here. Oh. Yeah, you got it?
Yeah.
There you go. Yeah. So they're basically saying the product is 7 because it gives you that, and then it's alpha 1 plus 1. Alpha sub 1 plus 1 is equal to 7. So R.
Okay, that's where I was getting stuck. So because 7's prime, the only way a product of positive integers could equal 7 is 1. Okay, that makes sense. That's that first step, because 7's prime, you can make this next one. Okay. So alpha sub j equals 6. So n is equal to p of 6. Now square it. You understand that part, right?
Mm-hmm. Yeah.
Okay.
Yeah.
Then n squared p12 is equal to 12 plus 1. 13. You don't get that one? That's the definition that's given in exercise 7.9 tau function.
Yep. I got it. I got stuck this part right here. These last two steps. I did not
get that now.
I did not think to do that. Yeah. Okay. Yeah, I got it. Yeah.
All right. Last one. We're gonna make it. Kind of. Nine. What is the smallest integer m greater than n squared for some n inside the natural numbers for which tau of m is odd?
Smallest integer m greater than n squared. Okay, so let's write that inequality on Miro. Wish I could have both up.
Brute force it. No.
For some n is greater for some. What is the for some symbol?
I don't know.
Is it like the inverted A or something? For some.
Isn't that for all?
No, yeah, you're right. That's for all. What is the for some math symbol? Oh, interesting. They use the same symbol. It says, oh no, hold on.
Oh, okay.
Oh.
So smallest integer m that's greater than n squared. Okay.
Interesting. There exists does not mean there is only one, i.e. there exists is different from there uniquely exists. So since there is no specification that there is exactly one such object until proven otherwise, you can read there exists as for some, if you like.
Okay.
Yeah, I'm just looking at this stack exchange, math stack exchange on here. How do you write for some? Because they're saying for every x is a subset of x would be, then they have the upside down a, which is the same as for all, but is for some the same as there exist? It seems yes, but is it yes for every time? So there exists is the backward z. Okay. Back to Miro.
Which needs to be greater than
T of m is odd.
n squared and odd. So that's what we're looking for.
Tau of m is odd. Okay, let me go back to the book. So can we just plug all of these in and then see which one yields you tau of m is odd?
That would definitely work. What is just the tau of n squared?
Tau of n squared is m plus 1 is less than or is greater than n squared. So n plus 1
by
is
itself.
greater
So like
squared.
my thought is
which
like
then
figure out what the tau of n squared is, and then what increment would make that odd.
Just blind guess, I would say C, but that's probably wrong. Let me actually try and work it. So
I think plus 1 would be a prime number, so the tau of a prime number would be even, because that's 2. Tau of some prime number should be 2.
hold on.
To the solutions.
No, don't cop out yet.
Okay. I'll pull it up in case I want to use it.
All right, that's fine. Don't tell me anything. I'm gonna try and solve this one.
Oh, tau of
Come
m
on,
is
brain.
Okay.
Come on, brain.
It's written wrong. It's just m is greater than n plus 1, but the tau of m is odd.
Hold on, I'm not listening to you.
What does it mean for the tau of m to be odd? The number of positive divisors. So it can't be prime.
M is odd. Tau of m is odd. Tau of m is odd.
It needs to be a All right. I cheated.
Okay, don't help me. Hold on.
Yep.
Just give me like another 5 minutes.
Yep. 5 minutes of silence, everyone.
Yeah.
Are you writing things down in the notebook?
Yeah. Oh, I'm writing them in the mirror on the right side. Wait, give me a second. I'm probably not going to get this in the next
That's not you.
minutes.
Where are you?
Here, I'll make a smiley face.
There you go. I'm watching now. Good. People can at least watch you.
Yeah. It's okay. So I'm trying to apply the same approach from exercise 8. So we had T of n is equal to 7, and then we found you could find alpha sub j was 6. So if we have tau of m is odd, and m is small with smallest integer m greater than n squared. So can I just say n squared? I can't. There's no way I can just say put m squared plus 1.
M squared plus 1?
No, n squared plus 1. I wonder if I could do n squared. Hold on. If I do n
Why would
squared
you want to
plus
do n squared plus 1?
1 second. What is tau of n squared? So we did, if I go 13 minus 1, so maybe I go in reverse. So say so n squared minus 1, and then do man, this is annoying. So let me go back to the other one. Give me this hint. Is if I use the same process as exercise 8 but in reverse, can I get it?
No.
Okay. How different is this? The approach to this solution? Is it like different?
There's some key insight about tau functions and whether or not they're even or odd.
Okay.
And then you use that.
Do we have that?
Increment in. No, it's never told us that.
Oh, well, fuck. All right. I'm not going to waste time then.
Yeah. So basically,
give it to me.
So the tau of m is only odd if and only if m is a perfect square. Because
what does that mean?
So like it's a square by itself. It's like x times
like
x.
Like 3 squared or like
n squared is a perfect square.
Yeah. Okay. Yeah.
And this is because divisors come in pairs, except for when the pair is itself.
So that was like some sort of lemma to the tau function that it gave us in this blue box. Okay.
And so because of that, we need to find the smallest perfect square above n squared, which is going to be n plus 1 squared.
Okay. I see. Wait, hold on. Okay. Why plus 1 and not plus some other factor?
Because that's the smallest one. If you think about squares, looking here, you have like perfect squares are going to be 1 squared, 2 squared.
Oh, yeah. Okay.
Squared. The next one's going to be n plus 1 squared.
Okay. I get it. Oh, that's gay.
Yes, it is.
All
right. So far, not enjoying the exercises of this book.
Yeah, we can't do anything. All right. Sick.
We might have gotten it gets better. Hoping it gets better in the next episode when we get into new content.
Can I read a little bit of the next one? Since
we're
not at an hour. Yeah, I just want to start reading. All right. Chapter 4, Introduction to Abstract Algebra. In the previous section, we introduced the fundamentals of number theory. Now we will move on to abstract algebra, which forms the core of modern cryptography. But you might wonder, why should we study abstract algebra? Consider the set of natural numbers z sub n. Excuse me. Naturally, we want to define certain arithmetical. Why arithmetical? Is that even a word? It's just arithmetic.
Yeah.
Certain arithmetic operations over z, natural set of numbers. Wait, no, z is integer set.
So.
Integer set z sub n, for example, having 3 and 6 belong to the subset of integer set of z sub 9. I would like to know what it means to add them. Naturally, one would say that 3 plus 6 equals 0 in the integer set z. Oh, modulo 9. Okay. I see. That makes sense. Since 3 plus 6 over z gives 9, which is congruent to 0 modulo 9. However, while such a structure is straightforward for such a set, we can define operations over much more difficult sets, such as elliptic curve points, which are fundamental blocks for many cryptography protocols. In a way, abstract algebra gives interfaces to objects, just like in programming languages where interfaces specify certain common patterns observed in different instances of this interface. Let us explore this concept on the previously defined set z sub n. We present the following lemma to show the properties of modular arithmetic. Lemma 4.1, suppose a, b, c belonging to this integer set z sub n. Then we have the following modular addition properties. With 1, addition associative, a plus parentheses b plus c is congruent to parentheses a plus b plus c. Outside of the parentheses, the c, mod n in parentheses. The order in which we compute pairwise sums does not matter. Okay. Addition identity, a plus 0 is congruent to a parentheses mod n. We always have an element which behaves like quote unquote 0 in the addition operation, or like in parentheses, or like quote 1 when multiplying. 3, additive inverse, a plus
minus a.
A plus, no, sorry, I'm just like thinking about the previous lemma. Additive inverse, a plus in parentheses minus a is congruent to 1 parentheses mod n. For any element a, we always have an element negative a, which quote zeroes out an element a. Okay. Addition commutative, a plus b is congruent to b plus a parentheses mod n. The order of elements in the addition operation does not matter. Okay. Remark, all these properties also hold for multiplication operation, but with one drastic exception. You know, be good to really internalize these lemmas is like working problems that use each individual lemma and then have the deep tutor generate those exercises.
That'd be a good way to do that. Like that'd be good exercises using deep tutor to generate exercises based on lemmas, and then
make those, because deep tutor has the ability to make Anki cards. Make the Anki card set so I can practice it on my phone, or like have it on my phone, then work it out on a piece of paper. That would be nice.
I'll try that this week.
Okay. Remark, all these properties also hold for multiplication operation, but with one drastic exception, the existence of the inverse element. So in other words, the multiplicative inverse property does not hold in integer set z sub 16 or z modulo z integer set z modulo 16. In abstract algebra, we explore algebraic structures defined by abstract operations. These structures possess specific properties that help us understand the behavior of their elements. By examining these properties, we can derive general principles and insights applicable to any mathematical systems. 4.1 groups. Let us jump straight to the most fundamental algebraic structure, the group. Based on introduction above, see groups and generators, and then generators simplify, or like expand the number set of groups, but still you retain the multiplicative simplification associated with the generator. Like that's going to be useful. And I don't understand how groups and elliptic curves combine in terms of like when you're doing a when you have a pair of elliptic curves, like a family.
Yeah, I have a pretty good intuition of groups because I've been in chemistry for so long.
Yeah, groups I'm okay,
I'm
but
curious to see how that transfers over to this.
Yeah. I just don't understand elliptic curves as well as I'd like. So hopefully there's some more on that. Based on the introduction above, based on the set G, we want some operation. Okay. Some operation, then some symbol for some general operation to have certain properties. Wait,
Yeah.
what is that?
What?
It's just a placeholder operation, right? Some
Which one?
operation. Looks like a crosshair. Page 35,
That's
second
addition.
sentence.
Group addition.
Oh, okay. Group addition to have certain properties which are specified in the following definition. Definition 4.2, a group denoted by G comma addition.
Parameterized by?
How do I read that symbol? Addition? Like G comma the symbol.
A plus B.
The first line of definition 4.2, a group denoted by G comma and then the symbol.
Oh, yeah, addition. Addition under G,
Okay.
I think.
Addition under G, okay, is a set with a binary operation.
Addition.
Addition.
Obeying the following rules, yeah.
Obeying the following rules. One, closure. Binary operations always output an element from G that is, for all A, B exists within the group G, parameterized by A plus B is a subset of G group G. Two, associativity for all A, B, and C belonging to the group G, parameterized by A plus B in parentheses plus C is equal to A plus in parentheses B plus C. So associativity. Three, identity element. There exists a so-called identity element. E is a subset of group G, such that for all A belonging to the group G, parameterized by E plus A equals A plus E equals A. Okay, so E is an identity element. Okay. Inverse element for all A exists within group G. There exists some B belonging to the set of G. Group G parameterized by A plus B is equal to B plus A is equal to C or E. We commonly denote the inverse element by, did I just say minus A? Why are they putting this in circles now?
Okay, so O. So I looked it up. The notation is typically read as G with the operation O plus, the group G under O plus, or G comma O plus. So I guess you can use like O plus or O minus or O multiplicative, but like I've always called it like so it comes from either circled plus or direct sum. So the direct sum is usually what I've heard from in other group theory classes and stuff. But it's basically it's the operation of addition in this space.
Okay. Okay.
So I guess the O plus is the generic term for that symbol.
Okay, so I read the other one, the last line of for inverse element, O minus A, or A inverse. Yeah. Wow, that's the same thing as A inverse?
In this space, in group theory.
That's a different notation.
Like, if you look at like, have you seen like,
I've never done any group theory classes.
Generators in elliptic fields, right? When you do like multiplication elliptic curves, those are actually additions in the curve.
Okay.
Similar type of thing, right?
So it's O plus?
Yeah.
Okay. Yeah, I haven't seen that O minus notation. I've seen the O plus, but I don't know how to read it. Okay. Quite confusing at first glance, right? The best way to grasp this concept is to consider a couple of examples. Example 4.1, a group of integers with a regular addition, in parentheses, integer set Z, comma. Okay, what do you say that is? It's just a plus?
I guess.
Okay, so it's plus without the circle.
It's the addition. It's a binary operation addition in the group, and like in the Z
I
space,
see.
Right?
I see. Also called the additive group of integers is a group. Okay. Indeed, an identity element that is E sub Z, where Z is the integer set, the group of integers, is equal to 0. Associativity obviously holds, and an inverse for each element A exists within, A is a subset of integer set Z is in parentheses O. So you say O addition or O plus. O minus. So O minus A. And then that is parameterized by?
The set to
Oh,
is
set
defined
to.
as.
It's defined as, okay. Negative A is a subset of
So it's
the
using
group,
the language
integer group
in
Z.
the integer space, basically. It's using the same group language and integer space. And so we know like the inverse of A in integers is
Yeah.
negative A.
Yeah.
So it's just showing the symbolism, the general
Yeah.
symbolism for the specific case of the set of integers.
Okay. I see. That's I've never used that notation for
It's
I've never
odd
dealt
because
with
groups are
groups.
different fields in a lot of ways. And so
I
how
see.
you add those things together is different than how you would add things within a given field.
Wait, hold on. Say that again. What you just said.
Like how you add groups together is different than how you would add elements of a group.
Well, you said field.
Yeah, same thing. A field is
So
a group.
when I think of is a field, because a field and a group are the same thing, right?
I think so. I've always considered them that way.
Okay, can we look that up before I internalize that?
Yeah, sure.
Okay. Remark: we use the term additive group when we mean that the binary operation is addition plus.
Okay. A field is a richer structure than a group.
A richer structure. Richer how?
A set with one binary operation satisfying associativity, identity, and inverse. So, for example, Z and the plus, the integers under addition.
As a group.
A field is a set with two binary operations, usually plus and multiplication. So a field is a group plus multiplication, basically. Like a group is just a single binary operation. A field is two binary operations, usually addition and multiplication.
Okay. That makes more sense. Okay, so we should not be using them interchangeably.
No,
a group and a field.
Today I learned.
Yeah, let's. Okay, now I've internalized that. Okay, so field is a richer group because it's two binary operations. Okay.
Yes, and in between there's
a finite field is
in between that is a ring.
A ring is the same thing as a finite field, right?
A ring is two operations, but multiplicative inverses aren't required. A field requires multiplicative inverses. So every field contains two groups inside it, but a field has more structure, two interlocking operations than a single group.
Is there a visual for this?
I'm sure there is, but it's not giving me one.
Can you prompt it and then throw it up? Because I feel like we can stop here. This is a good stopping point.
Yeah.
Yeah, because then it goes harder. A group is called an abelian, and then
it's using Figma to generate a diagram for me.
Nice. Man, this math shit goes hard. In the notation.
Hard, bro. Let's see. Let's blow this up. Blow that up. Make you go away. Make you bigger.
You might be constrained in the embedded.
Yeah, I can't do that. So
you might have to hit edit in Figma, and then you can probably blow it up there.
Yeah, I was hoping I just.
Oh no, there's a full screen. You see it? It's like really hard to see on the top right. There you go. You can control, control scroll. No? There you go. Okay, so. Okay, wait, hold on. It says it's mentioning an abelian group in the top right. Hold on, it's too far. We've gone too far. So what is the farthest left? What is that? A group? Yeah, that must be a group. And then the middle one is a field.
A ring.
Because it says add.
This is a ring. This is a field.
Oh, okay. I'm lost now. Okay, let's go from top left. So identity, one operation, associativity, inverses. That's a group.
Okay.
The middle one is
add
a ring.
A second operation.
So add a second operation. So a ring and a field both have two operations.
Yeah.
So X is associative. Two operations. R comma plus is abelian. Okay, so we don't know, or I don't know what an abelian group is. Do you know?
No.
Because we're about to read into that. Do we want to go over that real quick? And then this is where we leave off.
Let's just continue on. with this next time. We're already past the hour.
Okay. Sounds good.
Yeah.
Abelian groups. That's where we left off.
All right. See you next week, bitches.
All right. See you guys. Oh, there were people commenting.
There were
People like math. Hey,